First, a little bit of background on me. I'm a emeritus physics professor here at Frostburg State University. I retired almost a year ago, and very, very unexpectedly. I found out last April that the option was there for me to retire. They didn't force me out, and they offered me a huge sum of money, and I couldn't turn it down. So what can you do? You know how that is. But one of the things that I did as an emeritus professor is I still have access to my physics lab here, which is an advanced physics lab. And I have access to my Hewlett-Packard workstation system, which is what I'm using to do this presentation with. So that's one of the reasons why I stayed as an emeritus professor. I grew up in Cuyahoga Falls. Any Cuyahoga Falls folks there? I'm looking at the. I grew up in Cuyahoga Falls. My wife grew up in Kent, and I went to Stowe High School. And I was a member of the Cuyahoga Falls Club, and still am a member of the Cuyahoga Falls Club for about 50 years. So, I sure wish I could help you all out, because I am a CW operator, and I'd love to come and help you for field day. It's just kind of a long ways to drive out there to Portage County. But I can brag a little bit. If you leave me alone and just let me go, I can work 60 QSOs an hour. I can do a QSO every minute on field day. And so I'll probably just be operating, though, from my house here. I live up here in the mountains of Western Maryland. So if you see Maryland, I am extremely Western Maryland, up in the mountains, not down by Baltimore and Washington and all that kind of stuff. Okay, it's a fabulous radio location. I live high up on a hill, and so I have a great radio location. So I'm glad that I guess it's Mike invited me to come, and I want to talk about feed lines and transmission lines. It's the talk will probably be about an hour, because this is such a complex subject. And I do have a previous version of this talk that I have on YouTube. If you go to greglatta.com here, if you go over to greglatta.com, then that's my breakout site on the web. I have a music site, a mechanical engineering site, electrical engineering, and ham radio site. You can get a lot of information there, and I have travel videos and so forth. But let's get on to it today. Transmission lines and standing wave ratio is one of the most complex subjects you can ever address in ham radio, besides antennas. I think antennas are even more complicated than transmission lines. The first thing I should mention, though, is the different kinds of transmission lines that you've got. Most of you are familiar with coaxial transmission lines, and there are all different types of transmission lines. RG8 is probably the most common, or there's a 213 or something like that. There's also a small one, which is called RG58. That one is very, very popular too. But there are also other kinds of lines. There's twin lead and 75 ohm twin lead. There's what's called ladder line or window line. And then there are open wire lines, which is what I use in my antenna, which is just a line that I made myself out of number 14 wire, and I just used electric fencing insulators to make it. And you'll see that, excuse me, there are big differences in these. Some work better in some situations, others work better in other situations. But I want to dispel a couple of old wives' tales and misunderstandings right off the bat. Common question about coax, for instance, is why doesn't the coax radiate any energy? I mean, how does it prevent any radio wave from coming out of it? How does it go down the line but not come out of it? And my guess is that a lot of people think that the outer shield somehow shields and prevents the radiation from coming from the inner conductor. Well, that's 100% wrong. That's absolutely wrong. There is some shielding effect, but what actually happens is this. It turns out that if you have current in a tubular conductor, and that's what that shield is, it's a tube, okay? That current flowing down the middle of a tube behaves as if it were concentrated on a wire in the center. It acts exactly as if it were all exactly in the center. As long as the currents in the coax are equal and opposite. So as long as the current going in the inner wire is equal and opposite to the total current in the outer wire, they both produce an electromagnetic field, but they are exactly opposite in polarity like this, and they cancel. Even if you're hugging, even if you're right next to that shield, the two fields cancel and there is no radiation. Okay? It's the equal and opposite currents that cause the line to keep the energy within it. A similar thing happens with all of the twin lead types of line. You see here, there are currents in an open wire line are equal and opposite. Now, they're not exactly on top of each other. In the case of the coax, the wire and the effective shield are both on top of each other, so you get this exact cancellation. With open wire lines, you don't get that exact cancellation unless you're a few diameters away from the wires. So you can't take open wire line or ladder line and run it right next to the house. You should keep it at least 2 or 3 of its line spacings away from anything else to prevent any imbalance. And that's the problem with it. You can't bury it. You can't just shove it through a window. You have to do a little bit more to use these types of lines, but there are some big advantages. Okay, so it's all up to what you want to use. There's no such thing as a perfect line. Now, if you go to the ARRL handbook or any antenna handbook, here's a table of values that you can see here. I hope you can see. Can you see my red pointer okay there? You can see that red pointer. These are all the different properties of different feed lines out here. The most important one that I'll talk about is called the characteristic impedance. And RG8, RG8X, and RG8 foam, and there's a bunch of them here. They're all about 52 ohms, okay? And I'll talk about what that means. There's also something called the velocity factor, which I'll expand on. And then there's some other stuff here as well. You will notice that many of these have the same diameter. And this was standardized years ago in the military so that the connectors would always fit the different types of coax. Also, it's normal to say, why in the world did they come up with 54, 52 ohms, 51 ohms, 50 ohms? That, again, I believe came back from World War II, that they had to make it a certain way, and they said it's going to be nominally 50 ohms, and it stuck. And you'll happen to notice that this figure of the surge impedance of these popular coaxes is the same as the output impedance of your rig. There's a reason your radio is designed to work into a 50 ohm load. It's because most of the transmission lines that are out there are 50 ohms. And we're going to see that matching is a very, very important requirement. Your transmitter must see that correct impedance. And there's some other things here about the operating volts and stuff, but the most popular, these ones that you see here, RG8, and there's an RG58, and I'm going to show some of these here at the board in just a moment. I'm going to be switching between the computer camera here and the whiteboard, okay? And you should be able to hear me here when I move, assuming that everything works okay. And so I'm going to go over to here and move my chair. All right. Yeah, look okay then? All right. Now, one of the biggest questions that people have is, what is this 50 ohms? What does that mean? Okay. By the way, before I do that, let me show you some different cables. I pulled all these from my shack, and I use all of these in my shack. This is the window line. This is what you call window line or open wire line, but really this is ladder or window line. Open wire line would not have any of this plastic in between. It just has a spacer every so often, okay? So I call this ladder line. My transmission line that I use most of the time is 2 number 14 wires about this far apart, Okay, and I'm going to use that as an example. Then there are lines like this. My bet is a lot of you have got this line in your shack. This is RG58. It's very common in CV systems because it can handle about 500 watts. And it's very small, convenient, and less expensive. And in many cases, this is all you need. But for those of you who are running higher power, you're going to need a line such as this. All right. You're going to need something like this. This is RG8. This is also very common. This will handle full legal limit of 1500 watts. But here's an interesting question. Here's another line. They look exactly the same. For all intents and purposes, you think they're exactly the same, but they are not. This is a 50 ohm line, and this is RG8 or RG11, and this is a 75 ohm line. What is different about them that makes this one 75 ohm line and this one 50 ohm? And for that matter, this one is about 300 ohms. What is this surge impedance that they talk about so much? And we're going to see why is it so important. Now, here's what I like to do. I always like to do extreme examples. And I'm going to take a piece of open wire line, and I am going to make it extremely long. Extremely long. When I say extremely long, I mean 93 million miles out to the sun. This is going out to the sun. It's very, very long. All right. And I could make it just like that. It's a perfect transmission line. It doesn't have any resistance. It doesn't have any losses. It's a textbook transmission line. And I don't care if you take this line and you hook up a ohmmeter to it. If you take this piece of transmission line and you hook an ohmmeter up to it, I don't care how you hook an ohmmeter up to it, you're never going to get 300 or 400 ohms. There's absolutely no way you can hook up an ohmmeter to this piece of transmission line and get a reading of 300 or 400 ohms. There's absolutely no way you can get a reading of 75 ohms with this. So how in the world do they come up with this surge impedance? What the heck does that mean? Well, here's what it means. That is 93 million miles long. Here's the sun. Here's our sun out there. 93 million miles long. We're over here on Earth. How do you draw Earth? There's Earth, okay? 93 million miles. Now, that is a capacitor. It's two conductors. It's a big capacitor. It's a BMF capacitor. If you know what BMF means, if you don't know what that means, look it up. It's a big, huge capacitor. So if you try and hook up to this a battery, say a 9-volt battery, little transistor battery, you take a transistor battery and you hook this up to it, I think you all know what happens when you hook a battery up to a capacitor. There is this surge, huge surge of current, this as the capacitor charges. And so you'd think as big as this is, it would act like a short circuit. But it doesn't. It actually turns out the current goes into it at a specific rate. It charges up at a specific rate. In fact, if this were my transmission line that I'm using, which is about 4 inches apart, it turns out that this looks like a 600 ohm resistor. The current flows into it, and if you connect up to this, if you hook an ohmmeter here, the ohmmeter will read 600 ohms, provided this line is very, very, very long. If you take an extremely long piece of this RG11, and I'm talking about out to the moon, out to the next planet, that kind of thing, For the first few seconds, it will look like a 75 ohm resistor. And this is called the surge impedance. It's what a very long piece of transmission line would look like. And whether you hook up DC or AC to this, it behaves like a 600 ohm, in this case, resistor. And this is called the characteristic impedance. I can never remember if it's A or E, whatever, okay? And this is usually given the symbol Z. The British pronounce this naught. Z naught is the characteristic impedance. It's what a very, very, very long piece of transmission line looks like before it has a chance to charge up or anything like that, okay? And it turns out this is the most important parameter of the transmission line. Every transmission line has a characteristic impedance, and it is the most important aspect of it. Now I'm going to go back over here to the computer and trip all over this stuff that I got here on the floor. And the reason that it doesn't draw a huge surge of current is because not only does the entire assembly look like a bunch of capacitors all connected in parallel, but straight wire has inductance. Straight wire has inductance. And this sucker has got a lot of inductance. I mean, if it's 93 million miles long, it has a huge amount of inductance. The combination of the two determines what the characteristic impedance is going to be, okay? Now, there actually are formulas for this, and you don't have to necessarily know the formula, but when you apply the formula to it, what you find here essentially is that as you bring the wires closer together, the characteristic impedance goes down, okay? If you put a dielectric, a plastic, between the wires, like in this case, the characteristic impedance goes down. If you have coaxial cable, where not only do you have the conductors very close to each other, this thing's maybe half an inch, it's only a quarter inch between the center and the outer conductor. That increases the capacitance and lowers the characteristic impedance, and also the dielectric constant of the plastic affects the characteristic impedance. Now, there's a formula you can get for any kind of situation, but the difference between this and the RG8 is that this has a different type of plastic and a different sort of plastic arrangement. I think if you cut this open, you'll actually see that there are lots of air pockets inside the plastic, which lowers the effective dielectric constant and raises the characteristic impedance. If you look at open wire line, you can see that if you space the line about 4 inches apart here, and you use number 14 line, which is what I have, here's number 14. Hold on. Here's my, can you see my pointer there? If I come over here to 4-inch spacing and come up here to number 16 or 18 line, it's 600 ohms. And this might be useful because in some antenna systems, you can use the transmission line to match impedances. It can be used as a part of a matching network, and you might need a specific characteristic impedance. And based on the formulas, you can make a particular one, or in some cases, you can go to a manufacturer and you say, I need some coax that's 150 ohms characteristic impedance, and they can make it for you. Of course, ridiculously expensive, but nonetheless, it can be done, okay? Now, the other important line spec that you might encounter besides characteristic impedance. You notice for all of the coaxes, the characteristic impedance is 50 to 100 ohms. There's some that are 93. I've got a 2-meter high-powered kilowatt 1500 watt amp from Moon Bounce that uses some coax in it for impedance matching. It's 93 ohm coax. Okay, you don't find it in your normal store. But there's also what's called this velocity factor. And you'll see for RG8, it's 66%. For open wire line, which is not listed here, it's typically 95%. And this is the percentage of light speed that a radio wave travels down the line. Light speed in a vacuum is 670 million miles an hour. Okay. But in glass, in transparent media, and in transmission lines, it can be much, much less. So in RG8, where the velocity factor is 66, it only travels 66% of its speed in a vacuum. It travels much, much slower. Okay, and you can see some of these are 75%, 80%. Lots of them are 66%, and so on and so forth. For those of you who are just using the coax to hook it up to your radio and whatnot, you don't really care about this. You do care about the characteristic impedance, but the velocity factor isn't important unless you're using the line in certain specific applications. And then the velocity factor can be very, very important. What this means is that the wavelength of the radio wave shrinks when it goes into the coax. And you can, one way to see this is if you have cars spaced out on the freeway and they're all going 60 miles an hour, and they suddenly go into a construction zone where everybody's going 40, what happens to the spacing between the cars? They get closer. And this happens exactly the same with the radio wave. The crests of the wave get closer together while they're in the coax. Normally, you don't care about that. But if you're making antenna arrays, if you're making matching networks, if you're making phased verticals and things like that, then you better take into account the specific velocity factor of the coax. And sometimes, I know how this is, you buy a piece of coax at a ham fest and you don't know what it is. Well, that's where one of those antenna analyzers can come in. I have an Mfj Antenna Analyzer, and using an Mfj Antenna Analyzer, I can measure these properties of the line if I'm not sure exactly what it is. Okay. Now, I'm going to go back to the board. Any questions out there yet? Is there any? Not yet, huh? Okay. All right. Let's go back to the board, and I've got to get myself untangled here. We are thoroughly messed up here. Okay, there we go. Okay. This is the kind of stuff I love because I can actually do this kind of, I have measuring equipment where I don't have to have it out to the sun. I can just have it 50 feet long and I can make measurements. But let's do this. Okay. What I want to do is take right in the middle of this baby, right in the middle, I'm going to hook up a DC voltmeter, okay? But this is one that is center zero, okay? So it's reads in the middle, 0 volts, and we'll hook this baby up, okay? And here's what I'm going to do. I'm going to take my 9-volt battery, and for 1 second, I'm going to hook it up to the feed line. 1 second. Now this is 8 minutes. It'll take 8 minutes for that pulse to travel out through space, hit the end of the line here near the sun, and then the question is, what happens to it? Well, about 4 minutes later, it's going to come down here. About 4 minutes later, you're going to see this voltmeter go up to 9 volts and come back down. It's a 9-volt battery. Anybody ever stick a 9-volt battery on their tongue? Okay. All right. I did it with a 45-volt battery. Don't do that. I had a headache for a week after doing that as a kid. Okay. Don't put a 45-volt battery on your tongue and go around talking like this for a week. Okay. Now, if you just do this and stand by, something remarkable happens. You'll discover that 8 minutes later, this thing will go up for 1 second and come back down again. The pulse travels down the line, and when it hits the end, it doesn't disappear, it bounces back. And it bounces back in phase. You'll see this read 9 volts, 4 minutes, boom, 4 minutes, it reads 9 volts. And in fact, if you just watch it, every 8 minutes, this thing will go, going back and forth. You only connect this up temporarily. When a radio wave travels down a transmission line and it's an open end, it bounces back in phase if it's an open end. The energy must go somewhere. So it bounces back. What you've actually done here is you've stored some energy in the line, and it will bounce back and forth forever, assuming there's no radiation losses and no resistance and all that kind of stuff. We're in the textbook world here, okay? Well, what have you say, okay, I know what I'm going to do. I know what I'm going to do. I'm going to short circuit this bugger. I'm going to short circuit it. I tie it together and I short circuit it. You say, that'll kill it, right? Yeah, that'll kill it. It's short circuited, it's gone. Well, I hate to tell you, nope. It'll come down. You'll see this go plus. 8 minutes later, it goes minus. And then, boom, it goes plus. And then it goes minus. When it hits a shorted end, it's reflected 100% out of phase. Holy cow. Shorting it causes it to bounce off and get inverted. Unshorting it completely opens it and it's reflected in phase. Keep that in mind. An open end, it's reflected in phase 100%, like a mirror. A closed end, it's reflected 100% out of phase. Which now begs the question, how do you get rid of it? Okay, how do you get rid of it? Well, if you think about this for a little bit, the next question is, what happens if I put a resistor here? Okay. What if you put a resistor there where R is equal to the characteristic impedance of the line? When the pulse comes down and it looks at this resistor, it thinks that the resistor is just another bazillion miles of feed line. It doesn't know the difference between the 600 ohm from this or a 600 ohm resistor. So what happens? Nothing gets reflective. No reflection. The load absorbs the energy and turns it into something else. In this case, turns it into heat. If that was an antenna with a 600 ohm impedance, it would turn it into radio energy and it would radiate away. So one of the conditions we see is, in most systems, you like to have the termination impedance the same as the characteristic impedance of the line, because then no reflections occur and the energy is absorbed by the load and everything is great. What happens if it's not? What happens if R is bigger than Z naught? In that case, some is reflected in phase. So some of it reflects. If the resistance is less, some is reflected out of phase. So some of the energy goes down the line, some of it goes into the load, but some of it gets reflected. Now that starts to cause a problem. It could be a problem, okay? Let's take a look at what happens in the case that this is the case, which seems like all the time it is, okay? So the reason we want to know Z naught is because that's what load we want to connect at the end of the line. And you wonder why most antennas are made to have an impedance of 50 ohms, so that with 50 ohm coax and 50 ohm line, or 50 ohm line and a 50 ohm antenna, none of the energy bounces back, which is what you want. But the question is, what happens to the energy that bounces back? Does it just disappear? What in the world happens? Well, this is where it gets interesting. What happens if I send a wave down the line? And what's really cool is you can do this with a slinky. If you get a big long slinky, you tie the slinky on one end. I would have done it here, but I couldn't find it. This is the wave we send out. We don't send a pulse. We hook up some RF here and we send this coming out, and it's traveling down here. It hits the end, and I don't care what happens. Let's suppose it's short. Let's suppose it's open. It bounces back, traveling the other way. All right. Now, in the case of your home antenna system, when you start to transmit, this reflection occurs, this potential reflection occurs almost instantly. But the point is, some point, these two are going to cross. They are going to encounter each other, and they are going to cross each other. And when they cross, both of these, by the way, because it's reflected, have the same frequency. They have the same amplitude. Remember, it's completely reflected. So the size of this wave and the size of this wave are exactly the same. They are exactly the same. What's going to happen when they encounter each other? Well, if you think about it, it's really great if you can actually do this. We can do that here in the lab. There are going to be places where the one wave wants to go up and the other wave wants to go down, exactly the same amount. And when that happens, they fight each other and they cancel. And what happens is, I'm going to draw the two waves on top of each other. There are places where one wave wants to go up and the other one wants to go down, and the result is there is no vibration at that point. If you take an RF, a radio frequency voltmeter, and you connect it to your transmission line, this is your open wire line. I use open wire because you can't connect a voltmeter to the middle of coax. You okay? Oh, Marie just checked in. Hi, Marie. Okay. All right. But with open wire line, you can just hook an RF voltmeter there. You hook an RF voltmeter at these points right here. These are points where the two waves always cancel each other out. These are called nodes. These are nodes. These are where the waves are canceling each other out. But then in between them are places where this wave wants to take it up and this wave wants to take it up the same amount. And so it actually goes up twice as high as it did before. And so we get this pattern where it goes like this. I'm terrible at drawing here. We get a big buildup of voltage in between these, and those are called antinodes. These are called antinodes. The voltage in this situation, the voltage at these antinodes is twice what any individual wave is. And if you go out to a facility that's using open wire line, and if this situation occurs, you can take a voltmeter and it will show nothing, then it will go up, and then the voltmeter will go down, up, down, up, down, up, down, up, down. And this pattern, by the way, is stationary. These points, the nodes and the antinodes, are fixed. And I know some of you know what this is called. This is called a standing wave pattern. We often drop the word pattern. We often don't use this word. And so you say, what the hell you mean a standing wave? It's not standing still. The waves are moving. Yes, the waves are moving and they're encountering each other and they're producing this pattern of nodes and antinodes on the transmission line. Places where the voltage is much higher than normal and places where it is much lower than normal. Now I've got a figure here that I can show on the computer, if I can keep from getting tangled again, that shows this. And here we go. Now, what they're showing on this graph is just the upper portion of the standing wave, just the upper portion. There's another portion here. This is where we have an open circuit at the end. So we have a buildup of voltage at the end. Then we have no voltage, lots of voltage, no voltage, lots of voltage, no voltage, lots of voltage, and so forth. If we have a short circuit, the same thing happens. It's just that the nodes shift a little bit. Instead of having an antinode here at the end where the voltage is high, it's low. Has to be. What's the voltage across a short circuit? It's zero. So you have to have no volts at the end, and then it goes up and it goes down and it goes up and it goes down and it goes up and it goes down and so forth. This is caused by the two waves encountering each other. And by the way, what happens when that wave hits the transmitter end? Well, it bounces back, and the energy is bouncing back and forth along the line like this. Some of it's going into the antenna or the load. More is being fed in by the transmitter, but as you can guess, it's a mess. This is usually you might think it's an undesirable situation, but it may not be. That's one of the things I hope you learn here today, is that it's not necessarily a bad situation. Now, what if you have a resistor on the end? Well, then the reflective line, the reflected wave, isn't as strong. And as a matter of fact, what if the resistance was exactly equal to the characteristic impedance of the line? There would be no reflected wave, and the voltage would be the same. There wouldn't be any rise and fall in the voltage as you moved along the line or the current. It would be constant voltage anywhere along the line. The graph would be flat. And that terminology is used. You say the system is flat when all of the energy is being absorbed by the load. What's called a flat system. Okay. Now, notice here, the big difference is the bumps or the dips don't go all the way down to zero. They only go down to, in this case, about halfway. So in a flat system, they wouldn't go down at all. If it's open or closed, let me switch it here. It goes down totally to zero or extremely close to zero. And it goes up to about twice the normal voltage, okay? But if it's a resistive load, which is what we usually have, then in that case, the dips aren't as extreme. So we're going to hit one of the high points here of the talk. One of the things you want to know is how extreme is this standing wave? One extreme is where we have all the energy being reflected. Another extreme is where we have some of the energy reflected, and the other extreme, or we have none of it reflected, and then you have it in between, okay? So what we have to do here is go back to the board. And if we come back and we look at the situation where it's a resistive termination, okay, where it maybe goes like this. Like that. Now let me question. Okay.
I'm watching this.
You okay? Question?
Yeah, Joe's got his mic on.
Oh, okay. All right. Now, once again, what the hell does this mean? Well, if you worked at the Voice of America years ago, they used open wire line. They still do. Okay. These short wave stations usually use open wire line. You know what their open wire line is? It's 1/2-inch copper pipe a foot apart. They use plumbing pipe. Copper plumbing pipe is their transmission line, okay? When you're using 100 kilowatts, that's what you need. What I'm saying here is if you take an RF voltmeter and you connect it across here, it'll read a certain voltage here, then it will read lower, and then higher, and then lower, and then higher, and lower and higher as you move along the line. If you had coax, you could cut the coax, put a coupling in there so you can measure the voltage, and you could get something like this. Now, in this case, there's a maximum voltage, but there's also a minimum voltage. Okay? If it were a flat line, you just get this. There's no V max, there's no V minimum. When you connect your voltmeter across the line, it always reads the same. That's one way you could measure the system, is simply by going out. You run low power. You don't run 100,000 watts, but you run lower power. You put an RF voltmeter across this and you make voltmeter measurements, and you can see if it's going up and down. And that tells you whether or not it's terminated properly over here. But in this case, if you don't get any variation, it's matched. It's flat. You can see why it's flat. Okay. Here, the maximum voltage divided by the minimum voltage is about 2. This is about twice what the minimum is. If it dips deeper, the minimum is even smaller. Okay. The maximum voltage divided by the minimum voltage is called the voltage standing wave ratio. Or the voltage SWR. The standing wave ratio, this is the true standing wave ratio. It's the maximum voltage in the line divided by the minimum that occurs because of the reflected wave. In the case of an infinite impedance, if these dip all the way down to 0, if it's open or shorted on the end, the SWR is infinity, because anything divided by 0 is infinity. Now, this doesn't really happen in real life. There's always something that prevents it from being perfect. But an open or shorted line, the VSWR or the SWR is infinity. Ideally, you'd like it to be 1-to-1. Because the maximum equals the minimum. Anything divided by itself is 1. Here, the VSWR is 2, etc. Okay. All right. Now, when you measure SWR, let's talk about this. Okay. If some of the energy is reflected and going back, what happens to it? What happens to it? Is it lost? What the hell happens to it? Okay, well, nope, it's not lost. As soon as the SWR isn't 1, it means you've got energy traveling both ways along the line. And what happens is that energy goes back to the transmitter end and bounces off the end. Now, whether this is coax or open wire, it's the same thing. The energy, let's see, R isn't the characteristic impedance. You've got energy flowing both ways. So you've got a standing wave pattern. Your rig is here. What does your rig want to see? Your rig wants to see a 50 ohm impedance. But if you've got energy coming back here, when it hits the transmitter, it bounces back, and you have this situation where you have energy bouncing back both ways over and over again. Some of it gets into the load. The transmitter, meanwhile, is trying to feed energy in while it sees this other energy coming back. Needless to say, it doesn't like that. That causes the voltage here to be higher than it should be. Remember, if there's a standing wave ratio other than 1, the voltages and currents are higher than they should be. And if the voltage gets high enough here at the transmitter, it can damage those field effect transistors in your Yaesu or your Kenwood or whatever rig you're running. It doesn't want that voltage to be too high. And what will happen is protective circuits in the radio, if the VSWR gets too high, it will turn down the drive, limit the power going out, and not permit this to happen. Okay. So generally, you want to have the transmitter seeing a perfect load, but in this kind of case, it's not. Now, what actually happens is in equilibrium, if the transmitter is able to match it, some old transmitters, the tube transmitters in particular, essentially have an antenna tuner built in, and they could make adjustments. And of course, modern solid state transmitters have some antenna tuners in them. They're limited, but they can deal with it. They can adjust it and feed the energy in. So what happens is the voltages build up on the line, but energy is coming out, and the transmitter puts energy back in at exactly the same rate it makes its energy out. And ultimately, if it's a 100-watt transmitter and it matches it, 100 watts go in, 100 watts come out, but it bounces back and forth a bunch of times before it finally makes out. But this, we're talking about microseconds here. We're not talking about seconds. We're talking about millionths of a second. You don't notice this taking place. Okay. So the reflected energy comes back, hits this end, and it all winds up going back and forth. And the transmitter is going to have to deal with that by using a matching device or an antenna tuner. Now, here comes one of the biggest old wives' tales. Everybody is familiar with an SWR meter. Everybody's familiar with an SWR meter. Okay. Whatever, digital, whatever. I've got a beautiful digital one. There are some things that have been assumed here. First of all, it works only for 50 ohms. It works only for 50 ohms. It assumes that you are using a 50 ohm transmission line. If you're not, if you're using open wire line or ladder line or something, you can't use an SWR, the typical SWR meter for it. And further, it only reads the true SWR when connected at the load. If you want to know the true SWR of a system, you have to put this at the feed point of the antenna. Otherwise, it's not reading the true SWR. You've got to connect it at the load or a multiple of a half wavelength from the load. In other words, if you connect a piece of feed line between the load and the SWR meter that's exactly a half or two halves or three halves or four halves of a wavelength, it will read the correct SWR. I use this for my moon bounce antenna. I can't get near the moon bounce antenna. So I have some coax that it's a specific length long, and I hook it to the antenna, and then I can stand away from it and read the true SWR. How many of you have connected your SWR meter to the feed point up on your tower? Okay, most people probably have not. But here's the thing. We're not so interested in the true SWR. We're interested in the apparent SWR. This is what the meter reads. Okay. This is what we are interested in. When the apparent SWR is 1-to-1, if your meter reads 1-to-1, then the impedance is 50 ohms. This is what we usually do. When you adjust an antenna tuner so that your SWR is 1-to-1, you're adjusting it so that the apparent SWR is 1-to-1. And that is what your transmitter wants. When you do that, your transmitter will put the full energy into it. The actual SWR could be anything. The actual SWR could be anything. Okay. I'll give you an example just to show you how wrong you could be. If you have a 50 ohm antenna and you use some 100 ohm coax cable, okay, turns out here, this is mismatched. This is mismatched. There's going to be reflections. No matter what you do, there's going to be reflections. So you put your tuner here, and then your rig, right? And your SWR meter is here. But the actual SWR is 2-to-1. It's 2-to-1, not 1-to-1. Another case, if you used if you do this, and yep, I tried this when I was a kid. Just use open wire line and don't use a balun or anything. Okay, so you know you connect the shield here and up like this. I've done this. Okay, sure, why not? Okay, this is 600 ohm line, and then I've got an antenna system that's been made for a 600 ohm load. The actual SWR is 1-to-1. Line matches, no reflected energy, 1-to-1. This will probably show as what's 600 divided by 50? About 12. I think 12-to-1. This will show an awful SWR, and your transmitter absolutely won't drive that. Won't drive that. The key thing is you adjust your antenna tuner or whatever so that the apparent SWR is 1-to-1, and then everything will be okay. So what do you do in this case? You use a balun or you use an antenna tuner. And by the way, the tuner it doesn't tune the antenna, it matches the impedance of here to 50 ohms. That is what it actually does. Let me try going back to the computer here. Okay, we're just about done actually. All right. Now, so the question is, here's a question. Well, okay, if the antenna tuner can match it and make the apparent SWR 1-to-1, and we can feed energy into it, who cares what the real SWR is, right? Who cares? So what? All right. Well, it depends. Okay. All feed lines lose energy. This is one thing about all different kinds of feed lines. This is a table out of, again, the ARRL antenna book or whatever. And this shows how much energy the cable loses in 100 feet of cable. Now, I know a lot of you don't have 100 feet of cable. The shorter the cable, the less the loss. Keep your cable as short as possible. But you look at the differences here. RG174 is this real tiny, about 1/8 of an inch diameter coax. And at the 10-meter band, it loses 6 decibels, which is about 3/4 of the energy is lost in the line. You go to RG8, which I'm sure a lot of you use, That's down here. And at 10 meters, they're 100 feet only lose about 1.25 decibels. That's negligible. You go to open wire line, and even up to 150 megahertz, these things only lose like 1/3 of a decibel. So open wire line generally loses less energy, but you have to use an antenna tuner. But it loses less energy. It's more efficient, and it's a pain in the butt because you can't just bury it, run it against the house, and so on and so forth. But look what happens, and we'll finish with this. What happens if the true SWR is higher than 1:1? Now, with open wire line, if I go back to it, way down here, open wire line, even at 10 meters, doesn't lose more than 0.2 of a decibel. So if I go to down here at the bottom, if the additional line loss, here's the line loss when it's matched, 0.2 decibels over here on the extreme left. Even if the standing wave ratio is 10:1 on that line, you lose maybe 1.1 decibels, which is negligible. You don't care about it. That won't show up ever. 6 decibels is an S unit, okay? But look at coax. Look at if you use the RG58, which is common. Many of you use RG58. Whoops. Come on here. Hold on. Right here. At 30 megahertz, these typically lose 2.5 to 3 decibels per 100 feet, which means, by the way, if you got 100 feet of that thin RG58 between you and the antenna and you're operating on 10 meters, half of your transmitter energy is heating that line. You got a 100-watt transmitter, 50 watts of that is heating the line, and 50 watts are going to the antenna. Now, if you go and you don't keep that line matched, then you find if there's 3 decibels of line loss when it's matched, and if the SWR is, say, 7:1, you're losing an extra 3 decibels, which means in that case, 3/4 of your transmitter energy is being converted to heat, and 1/4 of your energy is getting converted into RF. And these figures become much worse. One of the things you notice, notice how all of the line losses go up with frequency. When you get to 2 meters here, you get to 2 meters, if you have 100 feet of RG58, you're losing 1/2 to 3/4 of your energy in the feed line. And by the way, this is true on receive. So if you're losing 3/4 of your transmitter going up, the receive signal is being knocked down by 6 decibels or more as well. Okay, so you want to keep feed lines as short as possible. You want to keep coax matched as close as you can. And with open wire line, as long as it's mounted properly, you got to use a tuner. Pretty much you can get away with murder. Okay. And I think with that, I don't want to go into matching networks, but I think it might be better if perhaps we take questions. Is that, who can handle questions here? Who handles questions from the restaurant there, from the American Legion Post?
Well, we do have.
Okay, go ahead.
We have the microphone here, so if anybody here has any questions, I can pass you the microphone. Any questions from the crowd? Anybody on Zoom with some questions?
Was I that confusing?
Maybe it was just that good.
Now, if you want to know what I use open wire line to a to 120-foot ZEP. It's 4 inches wide, number 14 wire. I get fabulous signal reports up into the Midwest. Just people can't believe it. I have a vertical antenna, and for that I use RG8, and I bury it in the ground. And I try to keep it adjusted as best, but I always have a tuner in line, because a tuner can take the slight mismatch and really keep the amplifier in the rig happy. And that's one thing. What happens with solid state radios is they want the impedance to be 50 ohms. They want that apparent SWR to be 1-to-1, and then they're very happy. If it gets above about 2-to-1 and you don't use the tuner, the foldback circuitry will sense the voltage is high, and it will cut down the drive on the finals and start limiting your power output. And that can be a problem there. With tube radios, tube transmitters have essentially a wide range antenna tuner built in, and they can handle a 3 or 4-to-1 SWR without any trouble. Okay, but now the modern rigs, man, it's so nice to go tune and it just locks it right in, matches that baby right up, and away you go.
I got a question.
Yes. Yeah.
How do you bring your open wire line into the shack?
I have a wooden board that mounts under the window, between the window and the sill. You know, it's about this tall, and then I just run a couple of screws through it. Yeah, it's close to the house, and you know what? When it comes down to it, I say, you know what? I can't do what I'm supposed to do by the book, so I do what I do, and I figure if the impedance is messed up, who cares? I can still adjust it. Okay, which brings up one point. I can mention that I mentioned that the characteristic impedance of transmission line depends on the capacitance. Those of you using window line, the plastic with the windows in it, you will probably notice that your SWR changes when it rains. And that's because when the water coats the plastic, it changes the dielectric constant, and it changes the characteristic impedance. I actually went to my own homemade open wire line because that was too much of a problem. Every time it got wet, it would shift too much, and if I was running high power, that could be a problem. So I went to true open wire line. But I keep it. I use. You can get plastic containers at the Dollar General or whatever, and use that to keep the line from being right against the house. There's all kinds of ways to do it. Okay, but it is more work than coax. Hell, coax you can do anything with. Yeah, there's a question there.
I got a question.
Yeah, shoot.
If
I'm
you're
retired, I don't have anything to do.
yeah, if you bring the open wire down, let's say to the outside of the house, could you go to a 4-to-1 ball-in and then go to coax, you know, running it through the house?
Okay, let's talk about balance. Okay, yeah, you could. In fact, in most antenna tuners that can drive open wire lines, they have a balun in them, right? There's no reason you couldn't put that balun outside somewhere and then use coax from there. However, one of the problems is baluns are designed, they're 4-to-1, but they are designed typically to match a 50 ohm impedance to a 200 ohm impedance. Now, can it match a 100 ohm impedance to a 400 ohm impedance? Probably, but it wasn't designed for that. And if you start running high power, it can start to be heated. For instance, this is the example I give. You can go down, if you got an old transformer, you got a 120 volt transformer with a 500 volt secondary. And you say, I can run that on 240 and get 1,000 volts out of that. Would you do that? I don't think so. It'll burn up. Many of these balance, now I'm going to advertise a little bit. I use a PalStar antenna tuner. And in a PalStar antenna tuner, they put the balun at the transmitter, directly at the transmitter. So the one side of the balun is truly at 50 ohms because the indicated SWR there is 50 ohms. And then what PalStar does is the entire tuner, all of the capacitors, inductors, and everything are floated above ground. And there's no balun on the output side. So that balun is always run within its specifications. It never overheats. There's essentially no loss in it. But you have to insulate the capacitors completely, and it takes a lot more work to do it. But once again, it comes down to whatever works. If you can get the energy into it and things don't overheat too bad, then what the hell, go with it. I tried using an antenna tuner on 160 meters. And this was one that I built. And I found that the balun on the output got warm. It got hot. And that meant I was losing a lot of energy in the balun. That was not acceptable. That balun was way, way, way out of its specs, and I had to come up with something different. But yeah, you could try that. I mean, this is why there's so many different ways you can do antennas. You could try that, see how it works. There was another question I know someplace.
Yeah, I got it. Most of the coaxes you talk about are HF.
Right.
Can you suggest one for VHF?
The one that I'm using is, and of course, there's two things. They get expensive, right? And the other thing is a lot of it has to do with one of the differences are, you see this braid right here. Okay. The less expensive HF coax just have the braid. But you look at this one here, there's a foil shield. There's an aluminum foil shield which shields it 100%, and then they have the braid, okay, and that prevents any leakage through there. The biggest problem, though, is the dielectric. The dielectric. What you're doing here with the plastic is that the electric field is changing. And this causes molecules in that plastic to rotate. And that's friction, and that's heat. If you look at some of these line specifications, one of the things that they are not listing here, but what you can look at is if you get a full coax properties table, it will tell you how many decibels per 100 feet are lost at any particular frequency. There's one, it's not listed here. I think it's called LR 400 or something like that. Yeah, it's in this table. It's just not, yeah, it's not listed on this particular table. The key thing is, whoops, get out of there, is how many decibels of energy to, I think it's LMR 400 to be specific, or LMR, something like that. I think that's the coax at VHF. It's very expensive. And you know what else? It's extremely rigid. There are the best lines. There's a line called Heliax for UHF and VHF, which is a pipe like this big. Okay, it's like a rigid, flexible pipe, and then inside is a solid conductor, and there's air or helium the whole way, and they have some discs in there regularly to support it, so that the insulator is air or nitrogen, water. If water should leak in at UHF, that can change the impedance. So they'll fill it with gas and then lock off the ends. But I think there's one that's called LMR 400 or something like that. That's one of the premium ones for VHF and UHF work. That's an excellent question, by the way. Thanks for answering it or asking it. Other questions there? Anybody online there? Well, thanks for having me, and it was a real pleasure. I wish I could come to a real meeting and enjoy dinner there. You know, it's looks like, is that the American Legion Post?
This is the American Legion Post.
That's
Yes.
pretty nice. Pretty nice. Yeah.
Well, sometime if you're ever back in the area, you know, always welcome to stop by PCARS.
Well, I'll tell you what, listen for me on field day. What I do on field day is, hold on a second here. I don't hunt for stations. What I do is I start to pile up and I let everybody come to me. Okay, so you'll probably hear me in there. I just operate from the house on field day. Any other questions or comments?
All right. Thank you very much for the presentation tonight. It was very informative and very enjoyable. This was excellent.
If you like so many other ones, let me know what you'd like, and I can work on them. And by the way, I did this one for the Cuyahoga Falls Amateur Radio Club, and I recorded it, and you can go to my YouTube channel. I've got a huge website, greglatta.com. I'm the National Weather Service observer for this area, so I've got lots of weather stuff. But then I've got a lot of ham radio stuff there on my electrical engineering pages. And I've also got a YouTube channel, and there are videos there. In fact, the person who asked about the balun, I've got a movie there that explains how one of those baluns works. And it will just surprise the heck out of you how one of those babies works. Pretty amazing. Well, I think it's time for a beer for me, maybe.
I think a few of the members here might be in agreement with that too. So, well, thank you very much again, Dr. Latta, for joining us. Really appreciate it. Glad to have you be part of the PCARS meeting this evening.
Well, it was a pleasure. This is the first one that I've done where we've had live people and we've had online. So it was nice.
Yeah, we're live. Thanks.
Yeah.
Thanks,
I
Greg.
saw you at CFARSA too. Is it Jim or is it Jim?
I'm
Oh,
Jeff.
it's Jeff. It's Jeff. Yeah. Yeah. You got 50-inch screen on there for your spectrum analyzer?
Yeah, for the K4. Yeah. Well,
that's
I'm
great.
getting old. I figured, well, I need that.
Well, I have a K2.
Yeah. Oh, yeah. Nice
And
radio.
I have a K2 that is an absolutely loaded
Yeah.
K2. Every option is in there except the antenna tuner. I've got the 100-watt amp on it.
Yep.
And I love it when I travel because it has every single thing that my big Yaesu has, except it's got it in a small.
Nice and
pack.
small.
Oh, yeah.
Yeah. I have a K3. It's loaded also. right
Uh-huh.
here.
Yeah, I
love it.
like Ellercraft stuff. I love
Made in
Ellercraft
America. I
stuff.
love it.
Yeah. Now, if you go to my webpage, I'm gonna have to get out of here. If you go to my webpage, I'm restoring an HW101. I got an HW101 that is one of the early run ones, unmodified, except for they put a SO239 on the jack instead of
Oh, yeah. I don't like those RC.
but otherwise, it's one of the early run ones, and I'm documenting the restoration of it. So check it out.
You-
Take
you
care,
get the-
everybody. I'm going to sign off, and we'll catch you later. Bye-bye now.